Okay, so well, good morning, good afternoon, and good evening, everyone. I can see in the attendee list that we have attendees from all over the world around, and it's a great pleasure for me to welcome all of you to our HAC webinar on photovoltaics in humanitarian projects. Today we have two very interesting talks given by Dr. Henry Louis. Dr. Henry Louis is a professor in the Department of Electrical and Computer Engineering at Seattle University. He has been working in the energy access field since 2008, and in 2015 he co-founded the nonprofit organization Kilowatts for Humanity. He was a Fulbright scholar to Copperfield University in Kitwe, Zambia, and now he's an associate editor for Energy and Sustainable Development and is funding member of the IEEE Working Group on Sustainable Energy Systems for Developing Communities. He has been recognized as an IEEE Distinguished Lecturer for his expertise on energy poverty and has spoken around the world on the topic. This will be the first talk, and after this we will have a short Q&A session. And the second talk will be given by Mr. Joachim Funk, who received this diploma degree in communication engineering in 1988. And he was working then as electronics engineer and later as group leader in the department and department head for the electronics engineering department at Insta Elektro GmbH & Co. KG in Germany. In October 1997, he began working at Nobile Incorporation in the Philippines and was head of the engineering departments in two different locations in the country. In 2008, he started working at Meditech GmbH in Germany, where he is the head of the technical department. And well, he has a great expertise in lighting fixtures, lighting technology, and solar power for those lighting things. Yeah, we will start with Dr. Louis. So I'd like to hand over. So the floor is yours. Thank you.
All right, thanks. Good afternoon or good morning or good evening, wherever you are. I'm in Seattle, and it is early morning over here, and I apologize in advance if my daughters come running in because they haven't quite gone off to school yet. So I'm Henry Louis. I'm as Christoph said, I'm a professor at the Department of Electrical and Computer Engineering at Seattle University, and I also run a nonprofit organization called Kilowatts for Humanity that does off-grid electrification primarily in Sub-Saharan Africa. So my talk today is really comes from my experiences both as a practitioner in off-grid electrification, but also as a researcher and educator. I do have a book on the material on this topic, textbook if you're interested. I think you can probably find free copies available on the internet if you look hard enough, but there's the link to some of the sellers there. So I thought I would start off by sharing some images of some of the projects that I've worked on to give you an idea of the size and scale and the types of applications that I've done and are fairly common. So the top one is a hybrid wind solar system that we worked on in Kenya, and you can see the two turbines here. I think we need to make sure we're all muted, please. Yeah, okay, I guess I'll just keep going. The bottom one is in Philibaba, Zambia. It's about a 2 kilowatt system, and inside that one room there is actually a small business that makes use of the electricity. And I'll talk a little bit more about the productive uses or the economic uses of electricity and why that is so important when we do off-grid electrification. Here are some additional projects. The top one was interesting because it was built in what we call a shipping container, and it was prefabricated, and then we moved it onto the site and then did the solar install on top of that. And the bottom is another building that runs there's a small business that operates out of it, making use of the electricity. In 2019, we did this solar installation in Sheba, Zambia. You can see most of the work that I've done has actually been in Zambia. And then finally, in 2020, we did a much larger system here in Kinshasa. And this system is unique in a couple of ways in that it's the first one that we did that actually also has a solar pump installed, and it powers a number of businesses in this building. So with that kind of an overview of at least giving you visuals of the types of systems that I've worked on, Let's go back to the beginning and talk about energy poverty. So energy poverty, quite simply, is the lack of access to modern fuels. And that usually means when we think of modern fuels, we think of electricity, and maybe we think of methane or propane or natural gas. Around the world, close to 3 billion people rely on solid biomass for cooking or heating. These are people that are burning wood, charcoal, maybe animal dung or crop residue. And close to 1 billion people don't have access to electricity. So that's about 1 in 8 people on the planet don't have access to electricity in their home, and probably about half the people on the planet don't have high quality or reliable access to electricity in their homes. So if we look at where we struggle with electricity access, it's of course not uniformly distributed across each country. About 500 or 600 million people without electricity live in Sub-Saharan Africa. The remainders are in South Asia and some pockets in Central America or South America. But we also should keep in mind that even in countries like the United States, there are pockets of places where we don't have access to electricity, primarily on the Native American reservations that we have here. The Navajo reservation, for example, has somewhere around 60 or 70,000 people without access to electricity here within the United States. Now, if we think about communities in general and their energy needs, we can break it into 3 areas. So if you're thinking about electrification, off-grid electrification, you might target 1 or more of these areas, and the system that you ultimately design will depend on if you're targeting households, community services, or productive uses. So if we look at rural households, the energy use in a rural household without electricity is primarily for cooking, heating the house, and for heating water. And so they'll use somewhere between 5 and 15 gigajoules per person per year. And this is far lower than the global average, which is closer to about 80 gigajoules per person per year. So if you're energy impoverished, you often use far less energy in general than the average person in the world. If we look at community services, we're talking about health clinics, schools, places of worship, community centers, etc. The electricity needs of these community services include lighting, both indoor and outdoor, and maybe some communication infrastructure. Now, if we drill in and look at the needs of a school, if you think about an electrification project there, you might be providing electricity for lighting, for internet, telecommunications, and computers, or ITC, as well as enhanced teaching technologies like projectors, powering printers, and maybe digital cameras. For health clinics, they have similar needs to schools, lighting, ITC, but then they also need refrigeration for vaccines and medicine, and also for special equipment like suction machines and diagnostic equipment, and any way of getting hot and clean water available to that medical clinic is also very, very important. And also, the reliability of a system for a healthcare facility is extremely important. So you might have larger batteries, you might have a larger solar system than you would otherwise. And then finally, productive uses. So the work that I do primarily is on this, productive uses of electricity, where we might power pumps or mills or some sort of forest or agricultural project product processing. You might be powering small businesses that are barber shops or sewing machines, providing refrigeration, that sort of thing. And what the research is really showing is that providing electricity to people's homes is important. It does improve quality of life, but if you want to make a substantial impact to the economy of the community and to make that off-grid system as sustainable as possible, you really should be powering businesses and organizations that make use of that electricity in a productive way, generating income, increasing productivity in that local community. And then that way, that income can also go towards maintaining the electrical system. So that's what we should really focus on, those applications whenever possible. So if we think about electrification, it's important to think of it as a continuum. So for some people, just having a small solar-powered LED light known as a solar lantern is enough to make a big impact on their life. They're transitioning away from kerosene, which is expensive and dangerous and low quality, to an electric light is very, very meaningful and actually can save them a lot of money. Now, of course, people generally want more than just light. They want to have electricity that they use for radios and televisions and, maybe many lights inside and outside. So for those that can afford it, solar home systems might be a good technology. So now we have larger panels, maybe 10 watts or 20 watts or even higher, and that is large enough to power an efficient DC TV and fans, etc. And then we move up to energy kiosks. So now we have several panels. We're usually in the hundreds or a few kilowatt size. And now we have enough electricity to power refrigerators and large appliances, powering small businesses, etc. But the energy kiosk usually doesn't include any sort of distribution infrastructure. There's no power lines running from one house or one business to the next. To do that requires a much deeper investment in planning the project and requires a lot more capital. So these larger systems that include distribution to households, distributions to community centers, etc., we usually call those mini grids. And here the quality of the electricity service is similar to that of the national grid. In fact, it is often better. It can be more reliable, and you can also power high power appliances in people's homes. Now, if we look at the off-grid solar market, it's large and rapidly growing. So if you look at the period from January to June 2020, you see how many off-grid solar lighting products have been sold, over 3 million. You look at the number of solar lanterns, solar home systems. So this isn't just small groups doing electrification projects out of charity. There are big businesses involved in this now, selling products and also installing these mini grids. Remember, mini grids are much larger systems. So depending on how you want to count it, there's somewhere between maybe 5,000 and 15,000 mini grids that have been installed in around the world. And this is just a chart that shows some of the details around it. So the potential there for mini grids is very large, with maybe 100 million or so households that can be served in Sub-Saharan Africa and Asia in the next decade or so. So now that we have a good idea of the context, let's drill down into some of the technologies. So I'll first introduce some of the system architectures that we typically see in these off-grid applications. So if we think about a mini grid, we can really break it up into 3 pieces. We have the energy production system, the distribution system, and the end-use system. And my talk today is really going to focus on the energy conversion system. The distribution systems that we use in mini grids are similar to what you might actually find your local utility using. There are transformers, there are power lines, there's protection equipment. The end-use systems are a bit different because we usually have advanced meters, or meters that are capable of pay-as-you-go, where the user can buy small bite-sized amounts of electricity before it shuts them off. But we're really, in this talk, going to focus on the energy production system. So the energy production system includes the energy conversion technologies. Usually there's energy storage as well, the converters, the controllers, that will model the other 2 systems, the distribution and end use, simply as a load here. So this is the architecture of a typical off-grid system, large or small. We have a PV module, or maybe we have several modules connected together in an array. We have a charge controller. The charge controller usually does 2 things. It tries to optimize the power production of the PV array, but it also prevents the battery from being overcharged. Most loads that we encounter in these off-grid scenarios, at least for larger off-grid systems, are AC because the appliances are more readily available and easier found than DC appliances. And so we have an inverter serving that load. Now, in some cases, when we only have DC load, like lighting or maybe DC appliances like maybe televisions, then we would maybe not need the inverter, and we would simply have the load connected to the DC bus. So this is what an off-grid system looks like in schematic form. This is what one might look like if you actually walk into the powerhouse of one of these off-grid systems. So this is a hybrid wind-solar mini-grid, so it's a little bit more complicated than one that would be strictly solar. But we see the charge controllers are here and here for the two PV arrays. This is the inverter. Because there are two wind turbines that produce AC, we need to rectify it before we connect it to the DC bus. And to prevent the wind turbines from overcharging the battery, we need to have a device called a diversion load controller, as well as diversion loads, which are simply high power resistors. Here are some other examples of powerhouses or control rooms in off-grid systems. Some are very, very small. This inverter you could easily pick up in the palm of your hand. And the one on the left is a much, much larger system where you have multiple charge controllers, multiple inverters mounted across this whole room. Now, what these pictures haven't shown is battery banks. And here's just a few examples of battery banks. At the left is a 48-volt battery bank, where each one of these batteries is a flooded lead-acid battery, 6 volts each, and they are connected in series. And on the right is a much larger battery bank. Each of these are 2 volts. And you can see just how many batteries we have. This is a much larger system. This is about a 60 or 70 kilowatt system battery bank, whereas the one on the left is about a 4 or 5 kilowatt system. I'm next going to talk about off-grid system implementation to give you an overview of the process. So if you or your organization is thinking about off-grid electrification, here I'm going to try to map out the typical steps that you would follow. Of course, every organization is a bit different. But broadly, what you start doing is you start prospecting and screening for a location to do your project in. Then you actually visit it and you collect more information through a site assessment. Then you make a decision on which community or communities to work in, followed by the technical and commercial design. And then you go through a pre-implementation phase where you are now lining up your vendors, getting your permits. Then you actually implement the system. And then you might be in step 7 for a long time, just operating. But at some point, you may decide you either need to expand the system or even retire the system. So I'll talk about each of these in a little bit more detail. So the first step is prospecting and screening. So here you're trying to decide which community to choose, because unfortunately, there's usually thousands of communities in a country that need electricity. So research really shows, and practical experience really shows, that how successful your off-grid system is, however you define it, really depends upon the location. So what are the characteristics that you're looking for to make your site successful? You want to be able to try to filter out the communities that don't meet those characteristics and only focus on those that do. And so some of the characteristics include distance from the existing electricity grid, the availability of solar or maybe hydro resources or wind resources, as well as other demographics like maybe income, etc. So your goal here at the end of the prospecting stage is to have a short list of communities which you will explore further for electrification. Now, after you've done that, you would actually go to the communities and do on-site data collection. So now you're investing more time and effort because you're actually traveling there, you're meeting with community officials, you're observing the community firsthand. And what you're trying to do here is make sure that the data that you've collected from one of these screening tools is reasonable. So maybe you used a database that you consulted or an online program that lets you identify communities. You want to make sure that that data is up to date. You might also do surveys and focus groups, and you start looking for locations where you might put your assets. After you visited those communities, you make some sort of decision on which community to do, or maybe if you're going to do multiple, you prioritize it. And there are lots of different methods for analyzing a particular project or a particular community, like pestle analysis or coming up with a theory of change, etc. Now, I just wanted to briefly talk about the characteristics that make a community attractive for electrification. So generally speaking, it's a community where the national grid is far away. And I say this because what you don't want to do is you don't want to invest, tens of thousands of euros on a program only to have the national grid come and make your system essentially a stranded asset. You don't want other competitors coming in and doing the electrification. You want to be in a community where the demand for electricity is high and that it is closely coupled with a productive use or a use that maybe greatly improves the quality of life, like a medical clinic. You want to make sure that people are willing to pay for the electricity. If you want your program to be sustainable, then there needs to be an economic component to it. You want to make sure that there's a suitable resource for generation. It's favorable if the houses are clustered closer together. If you want to serve them, it will reduce your distribution infrastructure costs. You want to make sure, or it's helpful if there's other supportive infrastructure like roads and a cellular network. You want the community to be politically stable, and you also want to get a sense that the community is such that vandalism and theft won't be a problem. So these are some of the things that you'd be looking for as you make that decision. Then comes the technical and commercial design of the system. Now here, what you're trying to do is you are co-designing the technical and economic component of the system. And it's often an iterative process, and you will decide, finalize a design that meets your technical or business needs. Maybe it fits your budget, or you're providing the targeted level of electricity access, etc. Or you might decide that it's actually not feasible to do this community, and then you would move on to the next one in your priority list. But once you've found a community and you're moving forward with the project there, then you get into the pre-implementation phase where you get permits, you're procuring equipment, which might take months, you're identifying who to connect and who not to connect, which is a very tricky and important part of off-grid projects, because most of the time you don't have sufficient budget to connect to everyone. So you need to decide who to pick, who to connect to, and who not to. And then comes the actual implementation, which can be just a few days, or it could be a little bit longer than that, depending on the size of the system. And then, of course, you need to commission it and verify it. And after you've installed it, the system is operating, you're serving users. You should be collecting technical data from the system, as well as commercial data and even social data. So is the system serving people the way they want to be served? Is it meeting their needs? What do they like about it? What don't they like about it, etc. And that will inform maybe your next system. And then you might come to a point where you want to connect additional users, and so maybe you're going to expand the system, or you might decide to retire it. And I think you should go into every project, every community that you're going to work in, and have a plan for retiring the grid. You don't want to leave lead acid batteries in these communities. You don't want to leave the equipment there. You want to have budget set aside for you to be able to return the land and environment to its original conditions. And then you probably will also need to do some community repair and relationships building at the end of the project as you exit, if you are in fact retiring the system. Now I'm going to focus for the next couple of slides just on the technical design piece here. So when you decide to do an off-grid system, one of the most important decisions that you make is what energy conversion technology to select. And it doesn't have to be solar. You could select wind, you could select a generator, you could select a hydro turbine. But these are the considerations that you should be thinking about. Is it sunny? Is it windy? What's the fuel cost and capital costs? what components will fail, how easy will it be to replace them, how hard is it for the community to operate it, how difficult is it to design, what are the environmental impacts, etc. Now, when we design systems, we have often we follow a numerical approach where we use a computer program to do an hourly deterministic simulation. So the designer comes up with the parameters of the system, the sizes to consider of the solar panels and batteries, what the load will be like, etc. And the computer does a simulation of it, and then you get results, and it's up to the designer to interpret the results both in a technical sense and economic sense. The problem with this is that I think we naturally tend to put trust in computer-aided design tools. But the real problem here is that if you don't feed in good inputs, if you put in garbage, if you're making bad assumptions about how sunny it might be or what the load will be, then the results of the computer simulation, no matter how sophisticated, are going to be incorrect. So you need to really spend a lot of time understanding the load, what electricity people are going to be using, as well as what the potential for generating electricity is, how sunny it is, etc. So one popular computer program that at least my organization uses is Homer, and you design the system and it will optimize it for you and give you simulation results. Now, if you don't want to use a computer program to do your design, there are several standards and guides that are available to you. Here are just a couple that touch on this topic, and there are others that are under development and certainly others that are under revision. And you should always view your design as iterative. We never get it right the first time. We always have to go back and question our original assumptions, work with the community, understand better their needs, and tweak our design. So think of it as an iterative process. And one way that you can improve your design is by, if you do multiple projects anyway, is to collect data from each one. And that the data you collect from each one will inform the design of the next one. So for example, we always install a data acquisition system with our projects, and we collect data like the temperature of the freezers, or the ambient temperature. We collect data about the solar power production, the battery voltage. And you can really learn a lot about your system from looking at, say, the battery voltage, how that changes throughout the day, the solar power, as well as the load. This is probably the most difficult thing to know ahead of time, is anticipating the power that the users will consume. So we collect a history of this, and we use that then to understand and better predict the next system that we implement. So I'll wrap up here with just some pictures of a system that we recently did in Zambia. So here's Zambia, and this location that I'm going to tell you about is in Kanchomba, which is in the southern province of Zambia. Yeah, it's right here. So this is the Zimbabwe border. So Kanchomba is an off-grid community that is, it's fairly remote, and there's power lines that pass through the area, but there's not a low voltage distribution line or anything that serves the community. So we worked with a partner to identify this community and meet with the community and come up with the requirements for the system, as well as identifying lines of business that the community could engage in to make good productive use of that electricity. And we ended up partnering with an organization, this youth center where there's about 40 young adults that ultimately have ownership and operate the system. We also know that Kanchomba is prone to droughts, and that the only well they have is this hand pump, and there's no irrigation of crops, etc. So we saw the opportunity for a solar pump. So after about a year of planning, we designed and had this system. This actually building was built for us. We had it built in the community specifically to house the solar equipment, but also each one of these windows is a business that makes use of that electricity. So each one of these windows is a business that makes use of electricity. So we have that economic impact in this community of Kanchomba. We start out our design with like sort of a sketch like this, where we communicate with the community through our partner to decide what sort of businesses they want to be powered by the electricity. We come up with a business plan, and then we sketch out our system. So in this case, it's a solar array. We have a maximum power point charge controller. We have a large battery system, an inverter. We have a data acquisition system, etc. And we have some cooling components. So we sketch it out like this. Then we do a detailed design like this, and we will then take this and send it out to licensed solar installers in Zambia. So this isn't Americans coming over and trying to save the day. This is us working with Zambian entities to install the system. So we send out a request for proposals to licensed solar contractors in Zambia. They're the ones that actually do the work. We select a winner, and then we help with commissioning. So like I mentioned in Kanchomba, that building was built as part of the project. And this is a way where the community can contribute by building bricks and doing a lot of the labor to build the building. And that's important for them to show that they want the project bad enough to commit labor to it. And so here are just some pictures of it going together. Here's a picture of the pump being tested, or the well being tested, to figure out how large of a pump we would need for the solar pump. And here's what our rendering of the building looked like before installation, and this is its near final shape. So there were some design changes, as you might expect, but it was fairly close to the original vision. And that's what it looks like completed. On the inside of this, here is on the left of the main components. So like you can see the inverter here. These are lithium-ion batteries. We decided to use lithium-ion batteries for their longer cycle life. And the next pictures that follow here are just pictures of some of the productive uses. So there's a chicken incubator here, and you can see a couple of chickens already have hatched. Here are the freezers going in for the small store that will be there. This will freeze fish and chicken, as well as cool beverages for people to buy. There's a barber shop. So here's the barber cutting this gentleman's hair. And that's the team that did the actual installation. So like I said, we rely on Zambian contractors as well as Zambian partners, like Fakani here on the left is our community partner. He did a lot of the liaison work with the community. So let me just kind of wrap up here. So close to 1 billion people lack access to electricity. And I believe that off-grid systems are viable in providing electricity access if done well. And one way that we can help the sustainability of these off-grid systems is by coupling them with productive uses like refrigeration, water pumping, sewing, chicken incubation, etc., so that it helps that community. They no longer have to travel long distances to recharge their cell phone. You generate income within that community and uplift people's lives. And I'd also say that although I did not touch on it so much in this, really understanding your local community, the community that you're serving through partnerships is quite fundamental actually to making these programs work. So I'll go ahead and stop there. There's my contact information. And yeah, thank you for your attention.
Yeah, well, thank you very much, Henry, for this absolutely interesting presentation. I have to say, I learned a lot because this has so many more aspects than I was thinking of. And yeah, so to the attendees, you can type in your questions to Dr. Louis in the chat. Meanwhile, I might have 1 or 2 questions myself. So when estimating, well, you showed this last project in more detail. Can you comment on how much time really goes in one project, from planning time to building everything up to the final?
Yeah, so we generally operate on like 1 year cycles. So my nonprofit, we do about one program a year. That's not to say it takes a whole year to do it. I think there's a lot of delays that come in with just communicating and gaining access to that local community. There'll be times, there's like 4 or 5 months of the year where you really can't get into the communities because of it's the rainy season and the roads are so difficult. But the actual design work on our end, we're volunteers, so it's not like full-time jobs, but we'll come up with a design of a system over the course of a month or two. Working, meeting about every week or every other week, and then that might get stretched out as we send questions out to our partner in the country to say, well, how many refrigerators might you be interested in? Or and that always takes time. It takes a long time to get a message to the local community and to hear back from it. The actual implementation, though, usually is about 3 days. And if we're on site, what we're doing is we're just commissioning it, making sure that the builder has built it per contract and making sure that everything works, as well as usually there's a big sort of festival that is associated around with it being opened. And then along the way, we're also doing surveys, or at least our partner is doing surveys. That's usually actually like the first step that we do. But usually we can get a project done in less than a year, but we usually only do just one a year.
Still amazing. I mean, a year for all this is great. Maybe I have a second question. So let's assume the site Germany section. We have been talking about this so many times because we do have a lot of students from abroad and also from Africa, and we do have some contacts to African NGOs, and we were always thinking about, well, making such a project ourselves. And just assuming we plan something, may we speak up with you to maybe cross-check our plans? I mean, you're very experienced in these things, and this might help us a lot.
Yeah, absolutely. And some advice I would say is that when you look for the community, make sure you find a partner that sits between your organization and the community. It's going to be very hard for you to understand that community, its culture, its values, the challenges and opportunities. So you really want to have a strong partner. And then I'd also just really emphasize that this is a fantastic opportunity for students to learn, but we really shouldn't be treating these local communities as a training ground for our students, right? So make sure that you keep that in mind, that this isn't an opportunity for students to learn how to wire solar panels, that there are people in whatever country you're working in that do that professionally and probably need that work. There are roles for students to play, but let's just make sure that we don't treat these communities as just simply training grounds for our students, that we were respectful and we look for every opportunity to build capacity in those communities.
Yeah, for sure. Now, what I meant was we have students that actually come from Africa and they have the contact. So
that's perfect then.
So we have good partners over there then.
That's great.
Yeah. So well, there's no other question in the Q&A chat.
I see some chats popping
Christoph,
up.
Yeah, if you look in the chat box, there's 2 questions at least, even more, that are in that section.
Basically, I cannot see them. So maybe
Okay.
you can see them.
Maybe it just submitted to the host. One of those is the case. Okay, so this one comes from Richard, who asks, well, his comment says, thank you for a very interesting presentation. How was the project in Zambia financed?
Yeah, so we are a nonprofit organization here in the United States, and we raise money through grants and individual donors. Most of our fundraising comes from individual donors that hear about our work and contribute small amounts and large amounts to our programs.
Thank you. Okay, and another one that I see here. Okay, this one comes from Francesca. Do you ensure the maintenance of your project partner in Africa? Are there some projects to teach people to repair the systems?
Yeah, this is what a fantastic question, right? One thing I try to teach my students is that everything that you install in the field needs to be maintained, and it will eventually fail, despite how well you maintain it. So you have to ask yourself, the moment we leave that community, if it fails, what's the plan? And so that's really why we work with Zambian installers that offer warranties with their work, and we have them bid on service calls. So what would it take? What would it cost us to send a technician to troubleshoot or fix the system? We've been, I think, fairly lucky in that really hasn't come up too much for us. We certainly budget it. We always have a sustainability fund where we keep project money in reserve to pay for replacement if the community itself doesn't save up enough money to pay for it. Solar systems like this, electrical systems, it's going to be challenging to find somebody in the community who can maintain it more than just cleaning off the solar panels and flipping breakers. It's going to be hard for them to do wiring, but there are electricians often in the nearby cities that can do that type of work. So usually we're protected first by the warranty, and then depending on the severity of the problem, either a local electrician might be able to help us out, or we will have the company that did the installation come back and service the components. But maintenance is extremely important, and you should have a plan and pathway for repairing equipment, because everything will fail inevitably at some point.
Sure, thank you. This question comes from Yannick. First of all, thank you for your interesting talk. How did your connection to Zambia develop? What made you choose especially that country? And also here, I'll just ask the part 2 of the question. What's the lifetime of the chosen battery cells, and how often do they have to be replaced in such a project?
Yeah, great question. So we decided early on that our goal as an organization wasn't to have as many projects in as many countries as possible. There is a very sharp learning curve to operating in a new country, even within a country, to understand the logistics, to understand the culture, to understand the language, etc. So we got hooked up through Zambia initially, because somebody at my university is a Jesuit priest who was stationed in Zambia. And so I just made the connection. He's actually an electrical engineer in addition to being a priest. So I went and visited him early in my career, and Zambia made a lot of sense for us because they're English speaking primarily, at least as a second language, politically stable, relatively stable economy. And then once you understand the logistics of getting into the city and building your network, and it doesn't make a whole lot of sense to jump around to different countries, because you now really understand what you're doing. You can execute projects really well in one country versus having to learn it all over again by going to another country every time. So we tend to stick in Zambia, although we do have done work in other places. The question about the batteries, it really depends. We found that flooded lead acid batteries seem to last the longest but require the most maintenance, and so we didn't like that maintenance piece because it was hard to get distilled water in to water the batteries, and to check it was problematic as well. So then we moved into sealed lead acid batteries, and we found that those lasted at good capacity for just a few years, mostly due to the high ambient temperature in the places that we work in. So although the manufacturer will say we last a certain number of cycles, we found in practice it was far less, mostly due to the elevated ambient temperature. So now the system at Kinchomba is the first one that we've done with lithium ion, and we're hoping to get thousands of cycles out of it, but we'll see. So it's ongoing for us, but I would say that temperature is the enemy of batteries, and that really learn how to interpret a battery specification sheet to understand how temperature affects the cycle life and its performance, because these are not being operated in temperature controlled environments like most manufacturers assume. So I hope that answered your question.
Great. So we've got another question from Joe. How do you identify partners and installers?
Yeah, well, we've been going to Zambia for well over a decade now, but we knew that the Energy Regulation Board in Zambia keeps a list of licensed solar installers. So after we come up with our design package, our specifications, we reach out to the people on that list, and I forget how many we started with, and by now we have a list of about maybe 5 that we know are going to respond to the request for proposals, and we work primarily within that group of say 4 or 5. But usually, I mean, well, in the Zambian case anyway, we could find the list of registered licensed solar installers, and then we also spent time, and we would do entire trips to Zambia just to make connections. We would go and we would visit them, not just the solar installers, but the equipment, providers, the vendors, etc. And then we also have partners in Zambia that can do that for us. So the pump installation, our community partner did all of that. They found that the contractor to do that. So a variety of ways, but staying in one country for long enough, you really get to know who the players are, and it's helpful.
Sure. All right, our next set of questions comes from Javier. Hi, Javier. Amazing presentation, Dr. Louis. Can you expand on the data acquisition system? Did you build it yourself or do you purchase it off the shelf? Also, what do you do if you don't have the communication infrastructure to monitor the system remotely?
Yeah, so we do both and have done both, built our own as well as relied on off-the-shelf data acquisition. When we first started, the off-the-shelf data acquisition was hard to come by and very, very expensive, thousands of dollars. And so we built our own, and we were sort of in the mode of building our own. That nowadays, the providers of the inverters, so we use Victron, and charge controllers, they actually have data acquisition capabilities built in. And so we Kanchomba, for example, we went with an integrated data acquisition system with the inverter charge controller. And that seems to be working well, although we always have sort of a research bent to what we're doing. So there's often data that they don't normally collect that we like to collect. So we might even supplement it with our own data acquisition system. Now, in areas where we don't have good coverage, it's a problem. It's still a problem. And we don't have a good solution to that. Our ideal is to get real-time data every minute set to us. And when we look at communities and locations to work in, that is a consideration, is the data connectivity. And although we wouldn't necessarily rule out a community because they have poor cell access, it is a consideration, and we might, a community might look more attractive than another if they do have cell access, just for that very reason. We'll just be able to monitor the system better if we can get data in real time and know if a problem is going to happen. Thank you.
Thank you. That's all the questions I see.
All right.
Thank you. Well,
thank you so much.
Henry, thank you very much again for this very nice presentation. Thank you, attendees, for all the good questions, interesting questions. And with having this said, I would like to hand over to Joachim Funk from Meditech to his presentation with the title Technical Design of Solar-Powered Electrical Devices.
Okay, good morning, good afternoon, whatever. I still have some technical problems here with the sharing, but trying to handle it. Okay, my presentation will be a bit different from the one of Dr. Louis. Dr. Louis' presentation, very interesting actually, was more about the bigger scale projects. Mine is more about the small scale projects, in particular small equipment of small solar equipment. First of all, again, my name is Joachim Funk. I'm working with Meditech GmbH in Germany, and we are producing all kinds of lighting fixtures, including solar lamps, etc. So that's what we're going to talk about now, or what I'm going to talk about now. So I will talk about the development of small-scale solar solar-powered system, and I will try to go a bit more into the details of the development of a solar-powered electric device. So when we develop a solar-powered device, first thing we need to do is to select the correct solar panel material. As you know, solar energy and solar panels are getting more and more in demand worldwide, and there's a lot of development activities ongoing from many different companies in many different countries. So what we see here now is the actual status quo that we have now. But of course, because of the very fast development of this of the solar technology, there is a lot of new things to be expected quite soon. So at the moment, the most common solar panel materials are monocrystalline and polycrystalline materials, as well as the amorphous one. The amorphous solar panel is the cheapest one at the moment, but it has quite low efficiency of around 7% only, meaning only 7% of the energy provided by the sunlight will be converted into electrical energy. There are also the better ones are the monocrystalline and the polycrystalline solar panels, which are a lot more expensive, but at least have 15 to 18% efficiency. And the monocrystalline has another big advantage, is that it has a good weak light performance, meaning even if the sunlight is not very strong, you can still get quite a lot of efficiency out of it, different to the other technologies. If you look in the table on the screen for the lower sections, these are the upcoming technologies. Some of them are like the gallium arsenide and whatever, which has very high efficiency. It's only for special projects at the moment because it's really very expensive. Later on, this might develop into something very interesting. But at the moment, we are, as Meditech, we are concentrating on the monocrystalline because of the high efficiency, the good value the value for money that we get out of this, and especially for the good weak light performance, which is very important for us in the northern hemisphere in Europe, where the sun is not shining every day, and we will go a bit deeper into that later on. So what is a solar panel? How does it work? Solar panel basically, and on the example of the monocrystalline solar panels or solar cell again, basically it's a semiconductor with a p-n junction, and it works like this: that the photons from the sunlight will kick out some electrons out of the semiconductor material, and if you design it right, these free electrons then can start an electric current. So this moving of electrons, which were generated by the photons from the sunlight, are basically the ones who are creating the electric current. So what you need are electric contacts then at the back side and the front side, and where you can contact your or connect your device or battery or whatever you want to connect there. And yeah, okay. So solar equipment, like a solar lamp or whatever, is in most cases is made out of 4 key components, which is the solar panel, the solar cell, of course, the battery, where to store the energy that you create from the solar cell, a load, but very important also the charge control, or the discharge control, we call it a battery management system, BMS. It was also mentioned in the presentation of Dr. Louis before, in a bigger scale. We use it for in smaller scale, like a cent coin or whatever in size. So these are the main components. And if you design electrical equipment, the solar powered equipment, you need to put these 4 key components together to design in such a way that they work together. It doesn't make sense to put a very big battery in there if the solar panel cannot provide enough energy, and vice versa. So you have to know the current that you're going to consume from your load. You have to design the battery in such a way that the battery will last long enough, or the battery charge will last long enough to let your light or whatever you want to run there run long enough. And also the solar panel, the solar cell must be big enough to load the battery in a reasonable time. But of course, also you should not oversize it. And you need to know also the battery voltage. Usually for the smaller equipment, we use lithium-ion batteries, which have a typical voltage of 3.5 volts. So all this has to be considered. And also the environmental factors have to be considered. You need to know where to use your equipment or your device. So there are a lot of environmental factors which need to be considered, to try to explain in the next pages. So the most important, the most known factor is, of course, the weather. Everybody knows on a sunny day you can generate a lot more electric solar energy than on a rainy day or a foggy day or whatever. That is obvious. But there are other factors as well which need to be considered. And for example, the latitude or the angle of incidence. So not all of us are living in near the equator where the sunlight hits the surface directly and can hit the solar panel or the solar cell directly. Usually, most people live either in the northern or the southern hemisphere, and the sunlight hits the surface in a certain angle, which is also depends on the season of the year. And as you can see in the picture on the left side, the solar energy or the solar rays in the northern and southern hemisphere are distributed in a much bigger area than, for example, near the equator. So you can only get a small amount of energy from the sunlight. Then you can do it when the sunlight hits the surface directly. You also need to consider the season of the year. For example, here in Germany, in summer, we have 18 hours of sunlight, while in winter, it's only 9 hours, maybe even less. So that means you have less time in winter to collect the energy from the sunlight. But there's also one other factor that you need to consider. Most solar-powered items turn off, especially solar-powered lightings, turn on in the evening when it's getting dark outside. And in winter, the sun is setting already at around 4 or 5 p.m. here in Germany. So that means the light turns on there at that time. And then when you come home from work, maybe at 7 o'clock in the evening, light is on for 3 hours already. And you might wonder that it's getting off already because the power that is stored throughout the day is already consumed within these 3 hours. First of all, because there's not enough energy and not enough time to charge the battery. And secondly, because it starts to discharge much earlier. So the charging time is getting shorter, the discharging time is getting longer if there is enough energy. So this one you have to consider also when you design your system. And you need to know that due to all of these factors, the solar energy in summer here in Germany or the Northern Hemisphere, it's in June, July, is a lot higher than in winter in January, December. So you can see here in this in the graph on the left side that there is the direct radiation and also the diffuse radiation that you can of solar power that you can get from the sunlight. So it's a lot lower in winter than in summer, of course. And you should never underestimate the difference of the seasonal difference because in general, I've collected this here in 3 graphs. The blue one is for clear sky, sunny days. The red one for partly cloudy days, and the green one for really cloudy days over the year. And if you don't only look at the blue line with a clear sky, with a sunny day, you can see that the energy or the usable sunlight that you have available in winter, in December, is only roughly about 5% of the one that you have in July and summer. So it's a big difference that you should never underestimate. And if you want to design a solar-powered device for the northern or southern hemisphere, the further more south or north you go, the more difficult it will get because the difference is getting bigger. So never underestimate this one and design your product in such a way that it will also work during the time when you want to use it. If you want to use it the whole year through, basically you have to design it in such a way that it will also work in winter when the solar panel or the solar power is not as big as you would have expected it before. So basically, you have to use a bigger solar cell to charge your battery. You also have to design it electrically. You also have to design your product or your circuit in such a way that you find the right working point for the solar cell. The solar cell has a curve, current voltage characteristics that you can see here on the right side. And as you can see, normally in this example, which is a standard size solar cell from Bosch Solar Energy, which has around 4.3 watts, and this one, if you run it with too much current, if you take out too much current, the voltage will break down. If you do not use enough current, then you have a good voltage, but it's useless because you don't have the voltage. So you always have to find a way to or design the circuit in such a way that you find the right working point electrically, so that you can really get this 4 watts plus that you can get out of this solar cell. You also need to know the spectral characteristics that you can see here on the upper side, on the upper right side, where you can see that the best spectral response of the solar cell is at around 1000 nanometer wavelengths, which is basically already infrared light. Yeah, you need to know also what kind of light that you have available, especially if you want to use your your equipment behind the glass or whatever. So the highest spectral response of a solar cell is in the infrared light spectrum. Before I was talking already about the weak light performance. So if you're not lucky enough to live at the equator, you have to consider also the environmental aspects that we discussed before, or that I explained before, and especially you need to know that you need to have a solar cell, a solar panel, which can still supply enough energy at a weak light when the sunlight is not very bright, so that you can get the most out of the solar energy that you have available. Then you need to protect your circuit. In the picture on the right side, you can see something that you haven't hopefully seen in actual. We all saw in the news in the past few years that especially lithium-ion batteries are quite sensitive for overcharging, also for over-discharging, and in worst case can cause fire. Some airlines even banned cell phones from their planes, or collected or asked them to put them somewhere to take out the battery or whatever, and several restrictions because of that. That's why it's important, especially if you use lithium-ion batteries, use a proper battery management system, a charging and a discharging control circuit that will prevent this case of fire or overheat or whatever it is, so that the battery will be charged in the proper way and also be discharged in the proper way, not too much and not too less, so that safety problems can be avoided. It's really dangerous. So battery management systems are available in ready-made circuits. We can see it here in two different kinds on the right side. One is this round shape, which is usually connected at the end, at the negative pole of the battery, of the standard batteries. And if you have a battery with built-in BMS system, in most cases you don't even notice it because it's hidden under some plastic foil or whatever, but it's there. And it should be there. And or other battery manufacturers prefer the longer type that we see on the lower right side, which can be put at the side of the battery. Depends on the size, on the kind of and size of battery that you're using. And if you look at the electric circuit in the middle of this slide, you can see that this battery management system is controlling the charging from the solar panel and the discharging to the load of the battery. So that's how basically these battery management systems work. Mainly this one these are ICs, which you can buy ready-made and then put a little bit of surrounding circuit beside it, like some transistors or whatever, so that you can have the proper protection of your battery, so that you can avoid any kind of safety problems from battery charging and discharging. Now we come to, especially for the smaller size solar systems or solar equipments. The solar panels are mainly made, or the solar cell manufacturers are mainly made for the big scale applications like the ones that Dr. Louis explained before to us. We can see on the left side this the typical standard size solar cell, which comes in a standard size of 156 by 156 millimeters and 4.5 watt power. For many items, this size is too big. If you design a solar lamp, you need a much smaller solar cell. And on the other hand, the standard solar cell has a voltage of only around 0.5 to 0.6 volts, which is way too low to charge a standard battery, because these panels or cells are designed for big scale applications where you put several of these the cells in serial connection. Then you can easily compensate for the voltage. But for us, we are designing smaller scales, solar lights and solar powered equipment. Since we cannot get always the right size that we need, we make it ourselves. We buy the solar cell that you can see on the left side and cut it into pieces, like you can see it on the right side. Of course, not manually, like it's shown in the picture. It is the cutting is by machines, fully automated, but basically you cut the standard cell into several small strips, and then you can connect it together again into new sizes, different shapes, and different voltages. You can compensate this 0.5 to 0.6 volts and connect it together into new voltages. For example, around 4 volts, which is quite good to charge a lithium-ion battery of 3.7 volts. So how to connect it? After cutting it, you make a series connection. Like in the picture below, they see 3 different strips that were cut beforehand, and then you can see that the back contact, the rear contact, is the first one is then connected to the front contact, to the bus bar of the second one, and so on. So you can basically, by choosing the right connection, you can then choose your own voltage that you want to create. And you can see here also in the picture that for the solar technology, the reason why the front contact is made by small fingers is that the sunlight has to go into the semiconductor, into the solar cell itself, to bring the photons from the sunlight into the semiconductor. That's why they usually use, or by the solar cell manufacturers, they're usually using these very small and slim fingers as contact, as a front contact, so that there's enough space for the sunlight to enter the solar cell itself, meaning the semiconductor. And so this is how to make smaller and custom-made solar panels out of this big standard solar cells and solar panels. Of course, afterwards, you need to connect to protect your custom-made solar panel. You can see here on the right side in the middle section several small strips already connected to each other, placed on a plastic board to make it mechanically stable, and then you need to protect it, the front side, from humidity, from water, from any kind of environmental hazards. So there are two methods, two standard methods to protect it. Either you use, like on the left side, you just simply laminate your newly made solar panel, or the second way is to put it into like a small basin, like that you can see it on the right side, and then cover it with transparent resin to make it stable and protect it. But it's an epoxy cover. if you use if you choose a location for a solar powered product, especially smaller ones, you need to know where to place it. And if you have, for example, if you put a solar lamp into your garden, you need to know what happens throughout the day to it. For example, if you place it there at noontime, then you might have very nicely illuminated solar panel, and then one hour after, the shadow of a tree which stands nearby might cover your solar panel, and you don't get anything out of it. So you have to know, have to choose a location where you can get most of the sunlight out of the sunlight which is available, and avoid shadows, and of course dust and humidity. So if it might be advisable, if you're living in a dusty area, to clean the solar panel from time to time, or or in winter, after snowing, brush off the snow so that you can that the sunlight can really reach the panel. Otherwise, it's useless. If you cannot find the right area in the area where you need your light, especially when it comes to solar lighting, if you cannot find an area where you need the light, but there's no sunlight during daytime available in that area, then use an external solar panel, like in the picture on the right side, and connect it with a lamp by using a cable, so that you can put the solar panel in an area where the sun is shining, where there's enough sunlight available, or enough solar power available, but put the light in the area where you need it. So that is only simple advice. And if you use solar product indoors, I mentioned it before already, please note that the biggest solar response of a solar cell is in the infrared light. And if you're using a glass which is reflecting infrared light, which is quite common, because many people don't want the inner of the house to be heated up by the sunlight. So normally the window glass manufacturers put some coating to reflect the infrared light to avoid the heat come in. Okay, this is just a small overview of how we design solar lamps and small solar power devices. I'm through now with the main part of this presentation. In the next slides, I will just show a little bit about our company, about Meditech, what we are and what we do here in Germany. Meditech is existing since 1998 now, more than 20 years. We are based in Germany, in Ense, which is a very rural area. But we have partnerships and factories throughout the world. Aside from our own factory here in Germany, we have 2 factories in China, one in Ningbo, one in Zhuhai, and one in Poland, in Vienna, where we produce different kinds of lighting fixtures. We have our own R&D. We have our own test equipment for all kinds of EMC, corrosion tests, IP tests, material testing, and so on, temperature testing. We all have that ourselves. We have a fully automated electronic production with a lot of machinery. We have automatic production lines with inline testing. That's important. Also, that means during the production, automatically the product will be tested if some faults or reliability or whatever. So here's just an example video of how this automated production line works. And just let the video run for a moment. It's not very long anymore. And see, everything is fully automated. Actually, this is a factory in China. And next one should be, not yet. There you can see already the inline testing. Here you can see the testing with all the LEDs of the strips properly lighting. So this is the production. And since we're talking about the IEEE Site Germany section, we're doing, together with Christoph Baer, we're doing some project at the moment. For example, on the left side, this solar-powered backpack, where the children, when they go to school, can charge a battery on the way to school, and where they can use the power stored in the battery, which is also built into the solar into this backpack, that can be used in the evening to make their assignment or whatever. We're doing some equipment which is already in the final stage now, which we call Crosschecking Alert, which is an alarm system for homeless people, and that these are some projects that we're trying to do together with the University of Bochum and the IEEE Site Germany section. Just some, on the next slides, I'll just go fast through it. Solar lighting, we talked about that already. So these are just a few examples of the many solar products that we have. We have general indoor and outdoor lightings. We have LED bulbs, accessories, Christmas lights, dog colors, letterboxes, and whatever. We have a big product, a very modern and nice product range of wood lighting fixtures, all with FSC certified wood. This one we are producing in our partner company in Poland. We have also classic materials, meaning cement fixtures, natural stone and cement lighting fixtures. We are supplying several supermarkets with supermarket lightings mainly for the shelves, shelf lightings. We are supplying cabin lightings for cruise ships, for different cruise ship companies, or actually for the wharves who are producing cruise ships. We have smart home products, different kinds, where you can control your lighting product with a smart home app. And we're quite proud of it that we don't throw things away. We usually, when there's a problem, we ask the customer to return it to us, and we rework it, repair it, and bring it back in the market. Of course, completely 100% checked and reworked. Everything safe and in good quality, of course. If you're more interested, you can look. We're on Facebook, we're on Instagram, we have our own website. Here it is. And now I'm through. Okay.
So thank you very much, Mr. Funk, for the nice presentation, and we gave some more technical insight to basically the electronics, which was very, very nice. Yeah, do we have any questions? So Juliana, you have to look basically into the chat because I cannot see it.
Sure. Perhaps we can wait just a couple of minutes to see if anyone has a question. Attendees, you can put that question either in the chat box or in the Q&A section. All right, we've got our first question. This one comes in from Yannick. What is the lifetime of a standard solar cell, and what is the most common reason of failure?
Well, for the solar cell, the lifetime is at least 30 to 50,000 hours. The failure of the solar cell itself is usually more on the mechanical way. For example, if the covering, the protection, which is on top of the solar cell, is fading out by environmental aspects, like from the rain or whatever, or if there's something really mechanical damage. So normally when we're talking about smaller solar-powered systems or equipments, the solar cell is not the one which will fail first. Normally, the part which is failing first in a solar-powered device is a battery, where the lifetime is a lot shorter than for the solar panel. So the solar panel is at least 30 to 50,000 hours using hours, or several years actually. So we have solar products, solar lightings ourselves. We are producing it for more than 15 years now, and we have customers who are asking for replacement batteries for 15-year-old solar lightings, where the solar cell is still very much intact.
Thank you.
Okay, so with this, I would like to thank the speakers very, very much. Henry, thank you very much for getting up this early. I know how that is, and but now you can start to the day. So Fung, thank you also, and we see in the picture also Mr. Köhler, who's the boss of Meditech. Hello as well. Well, thank you for both of you for the interesting talks, and I guess we learned a lot today. And Jean, I think this webinar is available online as well, because you have the recording. And
yes, they'll be available on demand.
That's pretty nice. And yeah, well, then also for you, Juliana, thank you for organizing this and for helping us with the technical things. And I'd like to wish everyone, well, whether a good day or a good evening or something in between. I don't know. So, and looking forward to stay in contact with all of you. Thank you.
Thank you.
Wonderful. Thank you, everyone. Thank you so much, Christoph.